Well, hello and welcome to lesson 2 of functions and transformations. In lesson 1, we looked at what is a function, and then how can we describe functions in terms of their domains and their ranges. And now today we're going to look at function notation. So we have a special way of writing functions that can differentiate them from relations. So notice in an equation such as y equals 2x plus 3, y depends on x, y is the dependent variable, and x is the independent variable. So y depends on x, and so we can say that y is a function of x. So as x changes, then we perform some operations on x, and that gives us y. So y is dependent on whatever the value of x is that we input into this equation. So if y is a function of x, and the equation actually represents a function when you graph it, then we will write this in a slightly different way, and we're going to call this function notation. So we want to note that a function, we're going to just give it the letter f. We're going to name it f. Some functions are named d or a or v or g or h. So you often name your function according to what you're actually measuring on the y-axis. So if we say that a function, we're going to call it f, is a function of x, where 3 times x plus 1 gives you the value of the function at x. So I'd like you to think of f at x, or f of x, as being read, that it represents the height of a given function at an independent value or an independent x value. So f at x is actually the height, and x is your input value. So if we want to say what's the height of function f at any given x value, and it's that you triple x and add 1 in this particular case. So we're going to say that f of x, or f at x, is going to replace y. Okay, if we were to look at a different equation where we're looking at d equals 3t squared minus 2t plus 1, then d is a function of t. Okay, if this is distance and time, then distance is a function of time. As time changes, it yields a different output value for distance. So we can say that the distance at any given time is equal to 3 times time squared minus 2 times time plus 1. Okay, so this isn't d times t. This isn't multiplication. We're saying that distance is a function of time, and that if you want to know the distance at any given time t, this is how you can find that value. Okay, so if we do the same thing for area, we can say that area is a function of the radius, and that as the radius changes, the area changes. So a at r, or a of r, is equal to pi r squared. And then v equals t squared minus 21. If velocity is a function of time, then we can say v at t equals t squared minus 21. A reminder that this isn't multiplication. This is a notation that changes an equation into something that we can recognize as a function. So I know that every input has at most one output value, and that velocity is dependent on time, and that this is v at t, or v of t, velocity as a function of time. Okay. So we're going to use function notation. It's similar to using x and y values. It's just that instead of x and y, it's x and f of x, okay, since y is the new f of x. So let's see how this becomes pretty handy. If I gave you the equation y equals negative 3x plus 2, and said find out what y is when x equals negative 1, then you would have to write sub in x equals negative 1 into y equals negative 3x plus 2. You'd have to write all that out. But here, since I've told you that f is a function of x, so f of x is equal to negative 3x plus 2, then I say, well, what if x was equal to something else? What if x was equal to negative 1? Well, we're going to find the height of the function f at an x value of negative 1 simply by substituting in negative 1 instead of x. So notice how we replaced x with negative 1 here in the function. So now we're going to replace x with negative 1 here on the right-hand side of the function. Okay, so then we just perform our operations here. We evaluate, we get 5. So f at negative 1 equals 5. That means that an x value of negative 1 will give the function a height of 5. So that this point would actually be negative 1, 5. If we look at the second example, we say, okay, same function f, okay, we've given it a name, this is f. F at an x value of 0, well, what height is the function f at when the x value is 0? We just substitute in and evaluate. So we can say that the function that we're calling f at an x value of 0 reaches a height of 2. So f at 0 is 2. Let's come up with a new function. This one we're calling it g. So g at x is negative 2x squared minus 5x plus 2. So let's find g at negative 1. Okay, so what's the height of this function when x is negative 1? We'll just substitute our negative 1 in. We'll evaluate, and we'll get a value of 5. That means that the height of g at an x value of negative 1 is 5. So again, this point would be negative 1, 5 as well. This is a different function, but it has a shared point there to the one we looked at a moment ago, f. We can perform all kinds of different operations using function notation. So if we want to know what is the height of g at an x value of 2, and then double that. Okay, so we can say find 2 times g at 2. Well, I'm just going to do 2 times, and I'm going to open up a big set of square brackets. And then in the square brackets, I'm going to evaluate g at 2. So we'll find out what is g's height when x is 2. We substitute our 2's in instead of the x's. We evaluate and simplify until we get negative 32. So that means that 2 times g at 2 equals negative 32. Okay, so this is a shorthand form of showing substitution. This shows the x value and then provides the y value as the output. So if the input is negative 1, the output here is 5. Now we can go the other way too. We were saying, what's the height if I know that x is negative 1 or x is 0? We can go the other way around, and I can say, all right, if I give you the height, I know what the height is. I want to know at which x value does that height occur. Well, let's look at an example. If we have f at x equals 5x minus 1 and g at x equals x squared minus 3x, then we want to find the values of x when f at x equals 24 is our first example. So since f at x is the new y, okay, so we can think of f at x and y as being sort of interchangeable in that they're both being plotted on the y-axis, then what I'm saying is that my function f at some unknown x value reaches a height of 24. Okay, so if f at x equals 24, then that's on my y-axis. The y reaches a height of 24. Because this still says x, that implies that the x is unknown. So we can figure this out. Since we know that f at x is equal to 5x minus 1 and f at x is equal to 24, I'm going to replace this f at x with 24. So we'll know that 24 equals 5x minus 1. And now we can actually solve for x. We can add 1 to both sides, then divide both sides by 5. So then we know that at an x value of 5, the height of the function will be 24. Okay, so we could say that f at 5 equals 24 for this example. Example B, it'll be the same thing. Function g at some x value reaches a height of 18. So again, we know the height, we know the y value. What we don't know is the x value. And since we know that g at x equals 18 and g at x equals x squared minus 3x, we're just going to use substitution. We're going to replace the g at x with 18 in this equation, and then we'll go ahead and rearrange, and now we've got a quadratic. So we'll factor it, and then if one factor times the other factor has to equal 0, then either the first factor has to equal 0 or the second factor has to equal 0, and then we can rearrange and isolate x in both cases. So really, g at 6 equals 18, or g at negative 3 equals 18. So we have these two different x values that will allow the function g to reach a height of 18. Okay, so we can either solve for x or we can solve for y, depending on what the situation asks us to do. We can also substitute one expression into the other expression. So we can substitute essentially one function into another. If we look at this example, if we say that f at x is equal to x squared minus 2x plus 1, I've just put a little blue highlight on the x's, so we know that f at any value would be that value squared minus 2 times that value plus 1. But what if we want to simplify f at x plus 3? So it's not f at 5 or f at negative 1, but it's rather f at some totally different binomial, in fact. Well, we're going to do the same idea. If we see f at x is x squared minus 2x plus 1, then f at x plus 3 will equal x plus 3 squared minus 2 times x plus 3 plus 1. Okay, so whatever is in the brackets with this f, that is what we're going to replace all the x values with. When it was a negative 1, we replaced all the x values with negative 1. If it's x plus 3, we're going to replace all the x values with x plus 3. And then we go ahead and expand and simplify. And then we can see that, okay, well then f at x plus 3 is actually x squared plus 4x plus 4. Now, given a graph, we can interpret the height at varying x values and interpret the different x values at different heights. So we'll just look through these examples here, a, b, c, d, and e. If I say that f at 2 is equal to some quantity, then what we're saying is the height of the function at an x value of 2 is unknown. So we know x is 2, but we don't know what the height of f is at an x value of 2. So we're just going to truck over here, there's the x value of 2, come over and hit the function, and it's at a height of 4 when the x value is 2, so that means f at 2 is 4. We can do the same thing for -1. If we know the x value is -1, but we don't know the height of the function at an x value of -1, we just truck on over, find our -1. Oh, there's the curve, boom. Now we're at a height of 1. So f at -1 equals 1. We can come over here and substitute that in. Same thing here. If we know the x value is 0, but we don't know f at 0, we don't know the height of the function f at an x value of 0, we go over and find it. Oh, it's 0. Okay, so that means that f at 0 is 0. We can go the other way around too. If I say f at x equals 9, then we're saying that the height, the y value, is 9, but that x is unknown. So we need to find out, if you go to a height of 9, what x value gets you to a height of 9? So we're going to truck up first to 9, and then we're going to look left and right, and we can see that, oh, you know what? At an x value of 3 and at an x value of -3, we can actually reach a height of 9. So there are 2 points where the height is 9. One is at x equals 3, another one is at x equals -3. We can do the same thing here. We don't know the x value, but we do know that the height of the function at that x value is 1. So we're going to truck up to 1, and we're going to look left and right, and we see that it's at +1 and at -1. And those are the 2 values that will correspond with x at a height of 1 for our function.